Welcome viewers, this is Mr. Odingo, and today I want us to learn about the evidences of existence of ion. And there are two main experiments we can carry out to find out whether ions actually exist. And with me here, we want to use copper 2 chromate 6 to be able to determine this compound is a green compound, an olive green compound. Now, if you dissolve it in water, you'll expect to make a green solution. That green solution is aqueous copper 2 chromate 6 solution. Now, we need to set up an electrolytic cell using a U-tube, a glass like you see here. This side, because let's say this side is the anode. So this is the positive terminal, this is the negative terminal. So this one is the anode, and then this one is the cathode here. So if we put the solution here of copper 2 chromate 6, we put it in this solution. I said it is green in color, so we expect this side to be very green in color. Now, once we close the switch, we expect the current to flow through this solution, and we expect that after dissolving copper 2 chromate 6, it will break or dissociate into two ions. The two ions will be copper 2 ions and also chromate 6 ions. And we know that copper 2 ions are blue in color. Copper 2 ions are blue in color, while chromate 6 ions are yellow in color. So we are going to find almost a range of three colors here. On one side, we are going to have yellow, blue, green. Green for the solution, the main compound, blue for the copper 2 ions, and yellow for chromate 6 ions. So once the solution is or electrolysis is going on, we know that these ions will separate. And we also know that the ions are attracted to the opposite charges. So it means that copper 2 ions, being positive ions, will be attracted towards the negative terminal, or the negative terminal, in this case the cathode. So we expect that on this other side of the electrode, you see I've indicated with dots here, we are going to see a blue color separating towards the negative terminal, and then the positive, the negative ions here, the chromate 6 ions, they'll be attracted towards the anode here. So we expect that on this other side here, we are going to see a yellow color, and this yellow color is due to the existence or the presence of chromate 6 ions, and then here will be blue, which is due to copper 2 ions. Down here, you see I've indicated the different indication here that this one is green color. The green is due to the presence of the compound, which is copper 2 chromate 6 compound. So this one tells us that ions are moving. Ions, the color moving towards this side will tell us that this ion is moving. We cannot see the ion moving, but we can see the color forming, the yellow color forming on this other side of the cell, and the blue color forming on this other side. Once blue color forms here, it is our conclusion that the blue color can only form there if copper 2 ions move towards that direction, and they move toward that direction because they are attracted there by the negative charge of the battery. And then here we see the yellow color, but the yellow color is just due to the fact that the chromate 6 ions are yellow in color, so they'll collect this other side, leaving down here a green in color. That is an experiment that you can do to be able to see that ions actually exist, and in this case the ions we are looking for are the copper 2 ions and the chromate 6 ions. The other experiment we can carry out to determine this is using aqueous potassium manganate 7, potassium manganate 7. So potassium manganate 7 is KMnO4. This is the compound. Now this compound, we know, people know it, and I know it's a very common reagent in the laboratory. It is purple in color. And the purple color is due to the manganate 7 ions, not the potassium ion. Potassium ions, they are colorless. So when you are doing this, we have to use it with what we call microscope slide. Microscope slide. So microscope slide, those people who do biology, we know what microscope slide looks like. So a microscope slide is a small glass. So we have a microscope slide here. We need a paper, a white paper. In this case, we can use a filter paper, or we can use chromatography paper. Any of those ones is okay. You can use either of them. Now, when you are using this paper, the first thing we need to do is to take a paper, a chromatogram paper or a filter paper, cut that paper in the size. The width of that paper must be the same as the width of the glass, but the length must be a little longer. So if I say this is the dot is the length of the paper, maybe there. So the paper is covering up to this part plus on the glass itself. So the paper will come from here up to that end there. Then we also need maybe 6 DC volts. So 6 volts DC, maybe a direct current of 6 voltage, a battery or a source that can provide us with that power. Then we need crocodile clips to connect this end here and to connect the other end here. So crocodile clips to collect that. But before we do that setup, we connect that setup that way, we need to ensure that the paper we have cut, I said that the length of the paper must be longer than the microscope slide, but the width must be the same. So after we cut it like that, we walk with it to a tap water, where a tap is, and we ensure that you hold that paper in this way, so that you pour water as water soaks the paper. You have to ensure you hold it there, you stop the water from running, and you ensure that you shake it so that no more drips of water are coming out. But you have to ensure that the water is wet, the paper is wet. So once you do that, the paper is now wet, you come and put it on top of the microscope slide. Then you clip the paper from each end using the crocodile clips. Assuming these are the terminals of the battery, this other side is positive, the other side is negative. You take only a small crystal of potassium manganate 7, only a very small crystal, you put it at the center. We know that the paper is now wet. So if the paper is wet, we know that it will dissolve potassium manganate 7, dissociating the ions into manganate 7 ions, and potassium ions. So what do we expect to happen? This manganate 7 ion being a negatively charged ion, it will be attracted towards the positive terminal, which is on the other side. So we'll expect the purple color, because this ion here is purple in color, the purple color will be seen moving towards that direction. It's not just one color, but it will be something like a cloud, a plum of a purple color moving towards the positive terminal, because this ion is being attracted to the positive side of the battery. And then we expect potassium to move the other side, only that we cannot see potassium, because potassium, as I've said, is a colorless ion when dissolved in water. So we are not going to see anything moving here, although if there's another way of determining, we'll see potassium moving the other side. But we can only see what our eyes can see, and that is the color changing. So the color that we put one small crystal here being purple in color, we'll expect a cloud, something like a cloud or a plum of purple color moving, a wave of it moving towards the other direction. That is giving us the evidence of existence of ions in potassium manganate 7. Thank you, viewers. These are the two experiments that you can conduct to really find out if ions exist. Last time we were able to look at the evidences that show that ions actually exist in some compounds, and we were able to use 2 compounds, and that was potassium manganate 7. We used it together with the microscope slide, and then we also used copper 2 chromate 6 with the U-tube glass that we are able to see colors spreading out to indicate that ions are moving. Today we want to conclude things to do with ionic compounds, and we want to study the physical properties of ionic compounds. And without wasting time, we want to look for the first property is melting points. Melting points of ionic compounds. And as the saying goes, ionic compounds are strong bonds, are strong forces of attraction. And so in their giant ionic structure, or in the giant ionic lattice, the electrostatic force of attraction holding the ions are very strong. It means that one ion is held to another ion using very strong forces of attraction. And therefore, those forces of attraction require a lot of heat energy to break. So one statement you can put across is that all ionic compounds have high melting points. But saying that is not enough, because are they having all of them having equal require equal amount of energy to melt them? The answer is no. While there are strong forces of attraction, the melting points are high. Some are higher than others, and that's why we can say that why are they higher than others. For example, if you talk about sodium chloride, you expect the melting point to around 801 degrees Celsius. When we talk about magnesium chloride, or let me say magnesium oxide, the melting point is much more than around 2,800, above 2,800 Celsius, above 2,800 degrees Celsius. So we can see that the melting point of sodium chloride is lower than this. Although 800 degrees is quite high, 2,800 is quite high. So we can see that the melting points are actually high, but magnesium oxide has a much higher melting point than sodium chloride. So mainly in examination, you will be asked why the melting point of magnesium oxide is higher than that one of sodium chloride, or any other ionic compound can be brought in. But what you have to know there is just look at the ions. In this case, we are talking about sodium ion being a monovalent, and then this one also being a monovalent. This is +2, this is -2. So we expect that this one, the charges between monovalencies, this is 1 and 1. We expect that this force, while it's very strong, is not as strong as the one in magnesium, because this one here now, the charges have doubled. In magnesium ion is +2, oxide ion is -2, sorry. So +2, -2, the force of attraction here will be stronger than when we have single charges in sodium chloride. That explains why the melting point of magnesium oxide is very high than that one of sodium chloride. So it means we need more heat energy to break these forces here, so that magnesium ions and oxide ion can be separated than we need in the first case of sodium chloride. But if you are asked to explain why ionic compounds have high melting point, we just simply say that they have strong ionic bonds within the giant ionic lattice, which require a lot of heat energy to break. So viewers, that is okay with that. The next property I want to talk about is electrical conductivity. Electrical conductivity. So electrical conductivity, what do I want to say? Do ionic compounds conduct electricity? The answer is yes and no. Why yes and why no? No, because in solid state, when ionic compounds are in solid state, ionic compounds in solid state do not conduct electricity. So the answer there is no. Ionic compounds do not conduct electricity. Why? The reason is that the ions are held in fixed position in their giant ionic structure. In our first lesson, we drew a cube which showed the position of ions in ionic lattice, and we saw how they are. So those ions are fixed in that particular position. They don't move. Since they don't move, electricity can only be conducted with particles that move, and those particles, in this case, they should be ions. So if these ions are in fixed position, held by strong ionic bonds, then we don't expect anything to move, and if they can't move, then no electricity will be conducted. But what about if you do something to make these ions move? And the only thing we can do here is either to dissolve them in water, dissolve the compound in water, or we can heat, we can melt it. We heat until it melts. What's the aim of dissolving in water or heating until melting point? We dissolve in water so that water being polar solvent, it is able to break down or separate. For example, if it dissolves sodium chloride in water, we know that water has 3 atoms. Oxygen is here. We know that this is partially negatively charged, partially positively charged, partially positively charged. So we expect that the water ions here, the oxide ions of the oxide ion in the water here, will be able to pull the sodium ions away, while this one's pulling that one away, meaning that the force of attraction holding sodium ions and chloride ions together can be overcome. Once they are overcome, the sodium ions will be free, the chloride ions will be free to allow electricity to pass or to be conducted. The same thing goes with when we melt it down. When you melt it, you are not using water to break it down, but you are using heat energy to overcome the forces of attraction holding the sodium ions and the chloride ions together. Once those forces of attraction are broken down, the compound changes to liquid. It is liquid because that giant structure that we drew before has now been distorted. We have overcome those forces, so we don't have a regular shaped structure, but we have something that can move any direction. It is now free to move. The ions are able to move from one point to another, and because they are able to move from one point to another, they can conduct electricity. So we say that ionic compounds don't conduct electricity in solid state, but they do conduct in liquid or in aqueous state. Now, viewers, the third property here is solubility in water. Solubility in water. Like I've mentioned earlier, when I'm talking about electric conductivity, these compounds can dissolve in water. They can dissolve in water because water itself is charged. It has both negative charges and positive charges. And we know that ionic compounds also have positive and negative charges. So these charges of the compound and those one of water interact in a way that the positive part of the water attracts, pulls away the negative part of the ionic compound, and the negative part of the water pulls the positive of the compound, making that compound to break apart. But that can only occur if we have what we call lattice energy and hydration energy. These two energies are very important. Hydration energy is the energy that can be offered, water can give to be able to break ionic compound apart, while the lattice energy is the energy holding two ions together. So if the hydration energy is more than the lattice energy, then you expect that water can dissolve that compound. But if the lattice energy is more than hydration energy, then you expect that compound not to dissolve in water. That explains why some ionic compounds don't dissolve in water, while others dissolve in water. For example, lead-2 chloride. Lead-2 chloride do not dissolve in water. But you realize that when you heat that water, then lead-2 chloride can dissolve. Why? Because now you have combined the force, the power of hydration energy with some heat energy, helping to overcome the force of attraction holding these ions together. But there are those ions, those compounds that don't dissolve completely, whether you heat or what. For example, when we talk about lead-2 sulfate. Lead-2 sulfate here, we know that there is a sulfate ion and lead ions. The force of attraction holding these two, we say, is lattice energy. The lattice energy here is much more greater than the hydration energy that water can provide to be able to separate them, and therefore that compound will remain undissolved. So that is about solubility in water. The last one is being brittle. We know that ionic compounds are brittle. What is brittleness? We have some terms here. We have malleable. We have malleable. Malleable is something that you can change its shape. You can heat it with a hammer, change its shape the way you want. But brittle is the opposite of malleable. When you try to change the shape of a brittle substance, then it simply breaks. Look at, consider a piece of chalk. A piece of chalk is very brittle. It's actually one of the most brittle things I've seen. You try bending a piece of chalk, it doesn't bend, but it breaks. But consider a bladder or something like a mattress. When you sleep on it, it kind of moves up and down to ensure that it gives you the space to do that, because then it's elastic. It can give you that space until you really strain it. But a piece of chalk, if it has to bend, then it breaks. That kind of thing that behaves like that, and others like glass can behave the same way, we say it is brittle. Why is it brittle? To explain why it's brittle, we have to go to, let me sketch something about structure. Let me just draw the first part of the structure, the front face. This front face has got this kind of charges. We know how to arrange them now. In the structure, they should be like this, keeping equal distance from each other and ensuring that the electron or the ions are alternating, negative, positive, and so on. What about if we kind of distort this shape? Distorting this shape meaning we apply some force. If I apply force here, or some stress or pressure, and I apply there, what happens? This shape kind of want to slide over each other. So if this layer here moves that way and this one moves this way, we are likely to have something of this nature. And if you have something of this nature, this is plus, minus, plus. This was minus, plus, minus. If we move this shape to distort it this way, if we move it this way due to pressure and it is distorted now, we realize that this one's alternating. But right now they are not alternating. We have positive, positive, negative, negative. What will that cause? That will cause what we call repulsion forces. And the repulsion forces, when you put two negative and two positive together, they now make the particle simply break apart because negative and negative cannot align next to each other. That is why ionic compounds are brittle. So please don't try to force them to bend, because if they bend, you are trying to make them behave this way and they will refuse. By refusing, it will break apart, and if it is a glass or a piece of chalk, you will be having it again. Thank you, viewers. That's the end of ionic compounds, and we'll be seeing you next lesson when we try to talk about